Okay, this is the third video in the CV or cyclic voltammetry analysis series for the inorganic class. So all of these videos relate to using and interpreting this template spreadsheet where each tab refers to a different type of analysis. So the first video, I walked you through how to plot a CV and interpret it. So that's this first tab down here. The second video, I walked you through how to interpret scan rate dependent cyclic voltammetry to evaluate the reversibility of the electron transfer or redox event and the mechanism of that event. This video is focused on using the same data, which is the scan rate dependent cyclic voltammetry, to evaluate whether or not a molecule is adsorbed to the surface of the electrode when it transfers the electron, or freely is diffusing and collides with the surface, which is an important point. And from that, we can then, based on that conclusion, we can evaluate what the actual diffusion coefficient of the molecule is, which is a really powerful tool. And so the way that you use this spreadsheet is to just input two columns of data. The first column is your scan rate. So same as before when you were evaluating reversibility and mechanism. So these are the rates at which you're scanning the potential on your electrode while you're conducting the experiment. And then these data are the peak current, and specifically the anodic current, though you could use either cathodic or anodic here as long as you have an nice symmetrical wave. Those are the two pieces of data you'll input into this template spreadsheet. Then this column will be computed, which is just a unit conversion from millivolts per second to volts per second, and then the square root of this column. And so in order for us to evaluate what the diffusion coefficient is, which is D here, that's ultimately what we want to compute, we first have to evaluate whether or not this relationship, which we call the Randles-Sevcik equation, is usable. So to do that, we have to evaluate that first question, which I mentioned. Is the molecule adsorbed to the surface when it transfers the electron, or is it freely diffusing? And that's a really important clarification, because if the molecule is adsorbed, then we cannot evaluate D using this equation. In fact, we just won't evaluate the diffusion coefficient. And that should make some sense, because if you look at the Randles-Sevcik equation, what it does is it relates the peak current passed in your circuit as a function of this big constant, which is a function of Faraday's constant and the gas constant and temperature, times the number of electrons transferred raised to 3/2. So here I have that as 1 electron, but if you have a 2 electron process, you would change this to 2, times A, which is the surface area of the electrode, which I've already input for you. This is almost always going to be 0.3 centimeters squared for this class if we're using classic carbon electrodes, times the square root of the diffusion coefficient, so that's our target, times the square root of the scan rate, which is an experimental variable, times C, which is the concentration of the analyte or the molecule in the solution, which you control. Notice here in this table of constants, I have 1 millimolar or 0.001 mole per liter. That's typically what you're going to use when you're doing your CVs in this class. But I have a second C here, which is actually the C that goes into this equation, which is just a unit conversion to make the units work out. So that's moles per cubic centimeter, moles per milliliter. So if you look at this relationship, what you notice is that the peak current is related to the diffusion coefficient here through all these variables. So if the molecule is not freely diffusing, if it's stuck to the electrode surface, if it's pre-adsorbed before the electron is transferred, then the diffusion coefficient is no longer relevant because it's not diffusing. And so that's why we have to evaluate first whether it's diffusing. And it sounds complicated, but it's not. All we need to do is make a plot of the peak current, which is this column, versus the square root of the scan rate. And so we get a plot like this. If this is linear, then it means this equation is functional, because this is a linear equation. If it's nonlinear, then it means that this equation does not hold up. There's something else contributing to the shape of this relationship. So when you plot peak current versus square root, if the R squared value is probably greater than 0.9, then we would say that the molecule is freely diffusing in solution when the electron is transferred to yield the current that we measure. So you check that box and you say, cool, I can proceed. If it doesn't, if it's a small R squared value and it has curvature, then you would cease to proceed. You would say, this is an adsorbed species and I cannot compute the diffusion coefficient. So if we proceed, if we have a relationship that looks like this is a nice straight line, then we can employ the Randles-Sevcik equation, and the Randles-Sevcik equation, it's no different. We're really just evaluating, in this linearized equation, we need to evaluate what this slope is, which is what I have computed down here. So this value, 0.000255, is the same as 0.003, it's just rounded here. And I have this automatically computing from this XY data up here. And you can see that the slope, if we look at this data, the slope is equal to all of these terms, right? It's y equals m, all of these terms in black, x, and there's no intercept here. The intercept goes through 0. So, so if we then solve for d, for the slope, then d is equal to the slope, m, divided by all these constants squared. So you can check my algebra, but this is what it relates to. And that's exactly what I have computed then for d here. So it's pulling all of these values in this expression to compute d, and now the diffusion coefficient is reported, and it's in units of centimeters squared per second. So this is the actual diffusion coefficient of the molecule in solution, which you're extracting simply from the peak current and the square root of the scan rate. And I tossed in a link to this online calculator tool, which can be handy to check your answers against. It's not a graphical way to do it, it's just at a single value. So using the Randles-Sevcik equation, you punch in one of your peak currents and you plug in these values and your scan rate, and it will spit out a diffusion coefficient. The diffusion coefficient's the same at all scan rates, right? That's why we get a straight line. And so it's a nice handy check on that. So that's how you would use the Randles-Sevcik equation and scan rate dependent cyclic voltammetry to evaluate first whether or not the molecule is freely diffusing. If the answer is yes, it's freely diffusing, then you can proceed to use the equation and you get the diffusion coefficient.